about linear regression in a little more detail than what we did with looking at the model back in class 2, where we didn't give it this fancy name, but not as much detail as if you were doing a statistics class or actually second semester calc. Your take-home quizzes today, I've handed that out. It's due on Monday. And remember, if for some reason you're not going to be here on Monday, you scan it or take a picture of it with someone's smartphone and send it in to me by 10:40 on Monday, or else it will be not acceptable. Okay, so let's take a look at today's material. We'll start, if you look at the top of the page, notice it's 2.3 and 2.4 and then supplemental material. Our book does not cover linear regression, and the 2.3, 2.4 is information about straight lines. And you've all had the equations for straight lines out your head by now. You've had many classes. We're going to do a quick review of this straight line business as we approach the line of best fit. We're going to just give you a little bit of a review with the demo, and then your class activities will take you a little further. For your class activities today, this is the order I would like you to do them in, just so that you have a chance to practice actually finding this regression line. So I'd like you today, when you write your class activities, I'd like you to do 1, 2, 3, and then I really want you to get to number 8 before you leave class. So if time is starting to run out and you're on number 2, or you see you only have 10 minutes left, scoot right up to 8. Because 2, 3, 4, and 5 is just review of straight line stuff, which you've already done quite a few times. Okay, so let's start with number 1 in the demo. So you want to start us off, Matt? Start us off. Matt's joining us, everybody. Matt, raise your hand. Yep, just read it. Yep. Okay, so this sentence is setting us up for being able to plot 2 points. And in order to do that, we need to identify what our variables are and which variable would fit along your horizontal axis and which variable would fit along our vertical axis. Remember, we call the horizontal variable our independent variable, and we call the vertical variable our dependent variable. So if you looked at that first sentence and the beginning of the second sentence, which part of which information given to you do you think would be independent, that we would have no control over? As the what? The weight diet we would have no control over? I see, maybe that wasn't a good way to say it. No, I'm saying maybe the way I asked the question, Di, wasn't right. Which of those variables that you see there are, excuse me, the numbers and not variables, 1989 and 44% and 1997 and 12%. Which of those numbers do you think would fit along your horizontal axis and be out of our control? They just, they're not, it's not dependent on anything else, I guess is the best way I can ask it. Jasper? The time. Whether it's 1989 or 1997 or 2015, you can't control that. Right? It's happening independent of us. The thing that's in this problem that depends on the time is what we're observing, what percent of the country is on this weight loss diet. Okay. Right? So the percent of that's on the weight loss diet is paired up with a year. So we should be looking for an ordered pair that has a year in it and has a percentage in it. Okay. X would be the year, but in part A, we've decided that we're going to say that the number of years that we're looking at will be measured with the base year being 1987, the number of years since 1987. So 1987 itself would be what year? What year, what value would we give to 1987? 0, because that's our initial starting point, right? So if we were looking at 1987, we would say x is 0, a horizontal variable. So along our x-axis or our horizontal axis, now you might say that you could call that t if you wanted for time. We'll just stick with y and x for now. So this is going to be the number of years since 1987. And then our vertical axis will be the percent of the population on the weight loss diet. Weight loss diet. Okay. So we don't know how many people were on the weight loss diet in 1987, but we could go up and translate the information given in that first sentence. By translating, we want to take it and we want to establish it with as 2 points that would fit on this graph. So let's see how we would translate this. 1989, 44%. We want to make that into an ordered pair. So we're saying that 1989, we want to translate that to an x value. Our x value is the number of years since 1987, so that would be 2, because 1989 is 2 years from 1987. And our percentage is given to us 44. So there we have a point, 244. Let's put it up here, 244. There we go. The second sentence starts off with some new information, another data point. 1997. 1997 is 10 years after 1987. So that point's going to be 10, 12. So I go over here on my axes, go over to where I would think 10 would be and put a 12, go up 12%. There we go. Okay. So again, as I mentioned, this is a review of the material in 2-3. We're going to find the slope between those 2 points. So we're going to draw a line between those 2 points and find the slope. Okay, so let's take a look at quickly reviewing the slope. So the slope asks us to find a rate of change, and it's a constant rate of change. Okay, so a rate means you're looking at a ratio, which means you're looking at a fraction or a division problem. So the first thing you do is you write your fraction bar, and you're looking at a change between 2 different variables, and that's why it's called a rate of change. The 2 variables you're looking at is the change in your y variable over the change in your x. And if you've been one of these people in the past that always kind of flip those by accident, here's one thing I would say to you, just as a little memory kind of thing. If you extend this in your mind, this x-axis to the left, you could think of this as like the fraction bar. Notice what variable is above that fraction bar, this fraction bar right here. It's your y variable. So that's what goes above the fraction bar. And what sits along the x-axis underneath is in the denominator. That's the only thing I can do to help you try to remember that it's the change in y over the change in x. Anybody else come up with another sort of thing that helped them remember? Rise over run. Some students remember. Anything else that you've used as a little sort of mnemonic? Jasper? Right. So you had no problem remembering that. Okay. Nick?
I had kind of spaced out, and I didn't see the part saying measure time in years since 1987, so I made 89 0, but I still got the same thing.
Yeah, the slope's not going to change. Right. Okay. So let's take our 2 y values, 44, and we're going to take away, we're going to subtract them. The order doesn't matter. You can say 12, take away 44 if you want. But what matters now is the order that you write the change in your x. So notice your first y value here is 44. So you want its partner, 44's partner, to be right below it. So when it was 44%, it was 2 years after 1987. Take away, and then what was 12's partner? 10. So this is going to be 32 divided by -8, which gives us -4 over 1, which most of us will just call -4. I always like to see my slope as a rate of change between 2 numbers, because then I can easily interpret it. So when I see -4 divided by 1, I put in my units here. And now, when that darn math teacher asks you to interpret it, you got all the information right here. So you could say for every year after 1987, or you could start with the top. There's a 4% decrease in the percentage of the population on a weight loss diet for every year after 1987. Okay, so it doesn't matter where you start. What's important is that you see both of these numbers here, the 4 and the 1, and then some word in your interpretation picks up the fact that it's a -4, like decreases, declines, and that you have the unit, which is percent, and then this 1 represents each year after 1987. So how you write your sentence, it doesn't matter. Remember, in your first project, you were asked to do this quite a bit. You'll be asked to do this again on a quiz and a test. So it's important that you get all of the information, and this will help you. So it's really up to you. Everybody in here would probably write the sentence a little bit differently. So we could say that for each year after 1987, what do we observe? We observe, yep, a 4% decrease of this country's population, whatever country it is, on a weight loss diet. All right. And as I said, you could have started off with, we observed that there's a decline in the percentage of the population, 4% each year after 1987. There's lots of ways to say it. Okay. All right. So the next thing we want to do is we want to find the equation for a line that contains those 2 points. Okay, we want to find an equation for the line that contains those 2 points. So those 2 points, 2 and 44 and 10 and 12, would be what we call solutions. Each of these 2 points are solutions to that equation, to whatever equation we come up with. Does anybody know what I mean when I say that the point 244 and the point 1012 will be a solution to whatever this equation is going to be? Could someone tell me what that means? We haven't come up with the equation yet. Can someone tell me what it would be if that it's a solution? I don't want the equation yet. Just what does it mean for 244 or 1012 to be a solution? I could plug in 2 where I see x and 44 where I see y. My equation will have a value for m and b. And what will that mean? It means that the left side will equal the right side. So both of these ordered pairs are solutions to this equation. Okay, so let's find this equation. Okay, so let's see. What do we know? We know the value for the slope. We know the value for the slope is -4. So we can start off by saying y equals -4x plus b. We don't have a graph with points in it to see where the y-intercept is. If we did, we'd know the value for b, because b is the y-intercept. B is the value of y when x is 0. You can see that right now by my taking my hand and covering up -4x. If x was 0, y is b. So that's the y-intercept. So we have to find the value for b. And this is the information we have. But it's not the only information we have, because we also have these 2 points. And each of those points lie on this line and are solutions to this equation. So a little birdie comes along and says, you can't solve this, Linda, because it has 1, 2, 3 parts you don't know. But if you have one equation and you can find 2 of those parts, if you know 2 of those values, then you can solve for the other. Well, here are 2 of those values. So you pick either of these points, it doesn't matter. I'm going to take 44 for y and 2 for x, and now I can solve this equation for b. So I'm going to add 8 to both sides to get b all by itself, and now I know that b is 52. So now I have everything I need to write out my equation in all of its glory. And if you're a little bit on the type A side, you would probably check by taking your other point, 10, 12, putting in 10 for x, negative 40 plus 52 is 12. You know you have the right equation. Okay, so that's the process of finding the equation for a straight line. Yeah.
Maybe I did do it that way in my head, but the way I kind of thought of it was just like, okay, 89.
You had slopes that were like these ugly fractions, and your intercept was like a number that wasn't really easy, like 52. It would be nice just to have the algebraic process down. Most of us can say, yeah, so if I go 1 year this way, I go down 4 to go from 1989 back to 1987, I have to take 2 steps, so I've got to go up 8 on my y-axis, which brings me up to 52. Yeah, and most of the time, you could just see that this line is going to continue in this direction. So your y-intercept, which is the value for b, has to be bigger than 44. So that is just another way to check on your sort of thinking about it. Yep. Yep, you could put a 12 in here and then its partner 10 in there, and you'd get exactly the same value for b. Yep, it doesn't matter which point because they're both solutions. Yep, the M has to match. Yep. Any other questions before we move on? All right, so let's explain the meaning of the y-intercept in the context of this particular problem. Okay, so the coordinates for the y-intercept is 0, 52, and we know that 0 corresponds to 1987, and that this corresponds to 52% of the population. And so there you go. Once you do that, you have your sentence. In 1987, 52% of the population was on a weight loss diet. Okay, in 1987, 52% of the country's population was on a weight loss diet. Okay, we've done this a few times in the past, but again, you want to make sure you have both the significance of what both of those numbers mean along with their units. I don't want a generic statement telling me what a y-intercept is. When I plug in 0, I get a value for y. We're talking about this context. Yep, Jonathan? Yeah, you're right. So according to our model in 1987, because it is an estimate, so thank you for that. According to our model, in 1987, we estimate that 52%. All the information that you'll be working with will always be estimates or predictions, because we're going to be looking at raw data, real world data, and nothing lines up perfectly in a straight line in the real world. Okay, if I had you go out and find data, which we used to do for project 3, you would find that your data, you couldn't get data that lined up perfectly unless it was already given a formula. Some people make mistakes with. They think if they look at like body mass index or something, all of this stuff was coming out in a perfect straight line. I said, well, that's because you're already using a formula, right? All right, so as I say, the y equals mx plus b form of a straight line is the most popular one. That line would be elected to the prom royalty, right? I'm not going to give it agenda. All right, find the point slope form. Okay, so this is another form of a line, and it's not as popular, but it's useful. This is where you know the slope and you know one point on your line. So you were able in the first part of this exercise, you knew 2 points, so you were able to find the slope, and then from there you found B. Sometimes you know the slope in one of the points. So in this situation, this would be the particular equation you would use. So let's see how we would use this equation given the information we have in the problem. We know that our slope is negative 4, and we actually do know 2 points, but let's suppose we were only given this point, 10, 12. Let's suppose we were given this information. Find the equation of a line with slope of negative 4 and the point 10, 12 sits on that line. All right. Then we would say, okay, I'm going to use this formula, and where I see x1, I'm going to put the number 10, because that's asking, x1 is asking me for a specific value of x, and where I see y1, I'm going to put a specific value of y. So this form is just as good as y equals negative 4x plus 52. It's just as good. You don't have to convert this to any other form. But often what people will do is they'll take this point slope form and they'll change it into y equals its equivalent equation, because that's what we're used to using for graphing. So the very next problem, G, asks you to do that. Write the equation from part F in slope-intercept form. So let's take a look at it. It was y take away 12 equals negative 4 times x minus 10. So if we want this in the slope-intercept form, we want to solve this for y. So before we do that, we want to distribute the negative 4 through. We want to use a distributive property on the right side. And now to solve it for y, we add 12 to both sides. And voila, we get exactly the same equation we got earlier, because these two equations are equivalent. They both talk about that line that we just drew a few minutes ago. All right, and then one of the things, once we have these lines in whatever form we want to put them in, we like to be able to then ask questions about our data set. And again, remembering, as Jonathan reminded us, that the questions we're asking here are predictions or estimates. We don't have the real figures. In fact, this data is just made up data. All right, we didn't give you real data. You have an example of real data that deals with global warming in your class activities. Okay, so use your slope-intercept equation to predict the percentage of adults on a diet in 2000. So when you see something like this, you know you need to find an x and a y value. One of these has to be given to you because your equation up here, in order to solve it, has two parts you don't know. So you notice you're trying to predict the percentage of adults, so you're trying to solve for y. We're asking you to solve for y when you know the value of x. And the value of x is going to be the number of years after 1987, which is 13. So for this problem, x is 13 and we don't know y. Okay, so to find y, we simply go to our equation and we substitute for x its value, and we get y equals negative 52 plus 52, which is 0. So what do you think about that model? It terminates there. Is it realistic, do you think? It's unlikely. And so this is what we talked about in class 2. If we go too far outside of our data set, we can often run into either answers that are nonsensical or answers that we don't really trust or have a good feeling about, or make absolutely no sense in like with the tuition data. Remember, we went back 8 years in our project to negative 8.13, and they said there was no charge for tuition and fees. So this is a mathematical model. It doesn't always make sense if you go beyond your data set. So this is an example of what we call model breakdown. Right? It makes sense mathematically, all the numbers fit, but it doesn't make sense in terms of what's going on. Okay, so then the other type of question you're always asked is, well, what if you know the value for y and you're trying to find x? So Ramses, could you help me with this one at all? What would I start with here? I have y equals negative 4x plus 52. Is there anything, any place I could put one of that number 50%? You know where I'd put it? Yeah, because that's what y's measuring, is the percent weight loss. So I put 50 where I see y, and I solve this equation for x. And when I do that, I get x is a half a year after 1987. Okay. So that, again, I hope should be a quick review for you of material that was prerequisite knowledge before you came into Math 107. But it's always good to get the cobwebs out from upstairs with a little dust brush, okay? So now we're going to move on to today's material, which has to do with straight lines, because our linear regression is a regression that uses a straight line. So we need to understand these pieces of an equation for a straight line. Okay, so if we assume that the percentage of adults on a diet declined by exactly 4% every year, no variation, and you can see that in this table, that as X increases by a unit increase of 1 year, the percent in the here decreases by 4, and it stays constant. That's exactly the type of thing that happens when you have data that fits exactly on a straight line. Okay, so if we were to draw the equation through that line, this line we already found, negative 4x plus 52, this is what it would look like. This is what all the data between, other than those 2 years we looked at, would be. Well, things don't line up perfectly in real life. Okay, we would really have data that would be scattered about this line. So one of the statistical plots that you look at when you put data into your calculator is called a scatter plot. So a scatter plot would look more like this, number 4. When we model real world data, we usually get a graph that looks like this versus one where there's perfect correlation. Okay, there's variation in your measurements. People don't always act exactly like you think they would. Okay, it's human nature not to have things line up in a perfect straight line. So what we try to do is we try to find a line that fits the data as best as possible. And there are mathematical things that you do to find that line of best fit. And for you, you're in luck because your calculator is going to do all that work for you. Okay. Now, some people took math back in the dark ages, and we had to do this all by hand. So, yeah, you may have to like go through a few calculations on your calculator, and you say, "Oh, I can't remember what button to press." You know that little violin we play. It's a lot easier than doing it all by hand. So you do have a huge advantage with GeoGebra or your graphing calculator or some other online software that will find that equation for you. Okay, so just be patient with yourself today when you're going through the calculator steps. All right, so here's the line we drew right here. The line we drew went through 2, 44, and 10, 12. That line has the equation y equals negative 4x plus 52. I want you right now, real quick, 10 seconds, draw a line through that data you think would be better than that line. Okay, I'm not going to look, just go ahead, draw a straight line through it. Use your ruler or your folder or your Math Studio bookmark. Just draw a line that you think fits it better. So when you think about trying to draw a line that we say is a line of best fit, what sort of thing are you keeping in mind? I mean, would you draw a line like this? Why not? You're missing the point, right? No, we don't want you missing the point in math class. We want it to be purposeful for you to attend, okay? We don't want to miss the point. It's not possible to put them through every point. So what do you try to do? Yeah, you try to include as many points as you can, and sometimes you can't include any of them, actually, but you try to get what? Huh? Yeah, but you can't put every point on the line. So the line of best fit, yeah, that's what it's called. The averages, what kind of averages? What kind of averages would you be? Now we're going a little bit beyond what you need to know, but that's okay. I'm actually just, all right, so let's say I put this line in. That line isn't as close. How are you measuring closeness? How are you measuring closeness to the line? Jasper? All right, so Jasper's saying he likes to have an equal amount of points on both sides of the line, if possible, right? That's what he's trying to do. But why would this line not be as good? Well, I'm missing the point, yeah, but I'm missing the point in this other line too. I'm missing a lot of points. What tells you? What are you actually trying to get? I'm looking for a word. Begins with a C. CL. Close, close. We try to get as close to all the points as possible. Okay. So I paid Molly to say that. She's going to get 2 extra points on her quiz and her paycheck, right? I know. All right. So if we put all of the lines that you drew on a graph, it might look something like this. Okay. So what we want to do is we want to find the line of best fit. I want to take that out. That's from the other class. This second sentence here in project 3, you can put a line through that. We're not going to do this project this semester. So a calculator or a computer is actually going to find this line of best fit. This line of best fit is sometimes called the regression line, or a it's not multiple regression, it's linear regression. So the best fit or a regression line, and look at how close our line was that we came up with. We came up with a line that was negative 4x plus 52. The line of best fit here is negative 4.3x plus 53.95. So we're pretty close. Okay, so let's look at a value you're going to be able to get from your graphing calculator. It's called the correlation coefficient. And we give the correlation coefficient the letter R. And the correlation coefficient tells us 2 things. It tells us the strength of a linear relationship and its direction. It tells us the strength of a linear relationship. So you couldn't use it for a parabola. It's for a line. And its direction. As you know, a line can either have a negative slope or a positive slope. So the fact that you have this R value, the highest value it could take on for perfect linear correlation in a positive direction, which means as X increases, Y increases. That's a positive association between your 2 variables. It's a positive slope. If I had data that lined up like this, its R value would be 1. If I had data that lined up in the second picture, it would be a perfect negative correlation. That value of R would be negative 1. And this says that as my X value increases, my Y value decreases. So this is a positive association between the 2 variables, and this is a negative association between the 2 variables. As one increases, the other decreases. Now, like you saw with our data, it usually scatters around the line. And if those points are fairly close to the line, you would expect an R value to be like 0.8, 0.9, 0.95. If it's really close, 0.98. If they start getting a little bit further away from the line, then that value gets closer and closer to 0. To have a correlation equal to 0, you would never try to fit a straight line through it, because I could draw a straight line through that in any direction I wanted. This would be an example. This scatter plot, that's what these are called, scatter plots, of data that would have a correlation very close to 0 or 0. And so you can't find any straight line that would be a possible estimate or predictor for that data. All right, so here's your class activities. We're going to continue to work with the data you've already been looking at. I want you to do 1, 2, and 3. If you came in late, you need to get to number 8 before you leave. So if you want, you could do 1 and 2, and if it's like 20 of, get to 8. I want you to be able to find the line of best fit with your graphing calculators, which I have up here. If you have any questions, just let me know.